NEC Section 680.51 applies to submersible pumps and other submersible equipment, mandating ground fault circuit interrupter, or GFCI, protection. While fountains receive explicit mention in NEC 680.51, the necessity for GFCI protection extends to other submersible equipment, encompassing submersible pumps like the one described. Addressing nuisance tripping, the NEC lacks specific directives. However, measures can be implemented to mitigate the risk of nuisance tripping. Firstly, utilize a GFCI breaker with appropriate ratings. Secondly, ensure correct installation of the GFCI breaker. Thirdly, prevent circuit overloading. Fourthly, opt for a higher quality GFCI breaker less susceptible to nuisance tripping. In instances of nuisance tripping, investigate the underlying cause and implement suitable corrective measures. This may involve scrutinizing the pump, wiring, and GFCI breaker for any anomalies or impairments. Moreover, adherence to NEC stipulations for underground feeder or off-cable installation is crucial. The NEC stipulates that UF cable must be buried at a minimum depth of 18 inches. The described scenario involves UF cable buried merely 6 inches underground and submerged in water, constituting a violation of the NEC and a potential safety risk. It's imperative to inform the customer of these NEC breaches and advocate for rectifying the UF cable burial depth. Furthermore, advocate for a comprehensive inspection of the pump and wiring by a certified electrician to ascertain proper installation and safe functionality. GFCI, or ground fault circuit interrupters, are crucial safety devices designed to protect individuals from electrical shock. These devices constantly monitor the current flowing through a circuit and compare it to the current returning. If there is a difference, even as small as 5 mA, the GFCI trips and quickly cuts off the power. This rapid response is vital because it can prevent a dangerous electrical shock from becoming fatal. GFCI protection is required in areas where there's a higher risk of electrical shock, such as bathrooms, kitchens, garages, and outdoor locations. Submersible pumps, being submerged in water, inherently pose a significant electrical hazard. If there's a fault in the pump's wiring or insulation, the water can become energized, creating a potentially lethal situation. By installing a GFCI breaker on the circuit that supplies power to the submersible pump, you're adding a critical layer of protection. In the event of a ground fault, the GFCI will quickly trip, cutting off the power to the pump and preventing a dangerous electrical shock. Selecting the right GFCI breaker is essential for ensuring proper protection and minimizing nuisance tripping. GFCI breakers are available with different trip current ratings, typically 5 mA or 30 mA. For most residential applications, a 5 mA GFCI breaker is recommended. This provides a higher level of sensitivity and will trip more quickly in the event of a ground fault. However, in some cases, a 5 mA GFCI breaker may be prone to nuisance tripping, especially if there are other electrical devices on the same circuit that generate small amounts of leakage current. In these situations, a 30 mA GFCI breaker may be a better choice. While it's less sensitive than a 5 mA GFCI breaker, it still provides adequate protection against electrical shock. Correct installation of the GFCI breaker is just as important as selecting the right one. The GFCI breaker should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. Make sure to properly connect the line and load wires, as well as the ground wire. If you're not comfortable working with electrical wiring, it's best to hire a qualified electrician to install the GFCI breaker for you. Overloading the circuit can also cause nuisance tripping of the GFCI breaker. A circuit is overloaded when it's drawing more current than it's designed to handle. This can happen if you plug too many electrical devices into the same circuit, or if you use a device that draws a lot of power, such as a space heater or a hair dryer. When a circuit is overloaded, the wires can overheat, which can damage the insulation and create a ground fault. To avoid overloading the circuit, make sure to distribute the electrical load evenly among different circuits. You can also use a circuit tester to check the current draw of each circuit. If you find that a circuit is overloaded, reduce the number of devices plugged into it or move some of the devices to a different circuit. Using a high-quality GFCI breaker can also help to minimize nuisance tripping. Higher quality GFCI breakers are typically more resistant to false tripping caused by electrical noise or other interference. They also tend to have more advanced filtering circuitry that can help to distinguish between a genuine ground fault and a harmless leakage current. While higher quality GFCI breakers may cost more than standard models, they can be a worthwhile investment if you're experiencing frequent nuisance tripping. The NEC, or National Electrical Code, provides comprehensive guidelines for the safe installation of electrical wiring and equipment. It's important to follow the NEC requirements when installing a submersible pump and its associated wiring to ensure that the installation is safe and compliant with local regulations. The NEC specifies the minimum depth at which underground feeder or UF cable must be buried. This depth is intended to protect the cable from physical damage, such as from digging or landscaping activities. The NEC also specifies the type of wiring that can be used for underground installations. UF cable is a type of non-metallic cable that's specifically designed for direct burial in the ground. It's resistant to moisture, sunlight, and other environmental factors that can damage other types of wiring. In addition to the NEC requirements, it's also important to follow any local electrical codes or regulations that may apply to your installation. Local codes may have more stringent requirements than the NEC, so it's important to check with your local building department to make sure that you're in compliance. It is critical to inform the customer of any NEC violations that you observe during your inspection. This will help them to understand the potential safety hazards and to take corrective action. In the scenario described, the UF cable is buried only 6 inches underground, which is a violation of the NEC requirement for a minimum burial depth of 18 inches. This could pose a safety hazard if someone were to dig in the area and accidentally damage the cable. You should explain to the customer that this is a violation of the NEC and that it needs to be corrected. You should also recommend that they have the UF cable buried to the proper depth by a qualified electrician. A comprehensive inspection of the pump and wiring by a qualified electrician is essential to ensure that they are properly installed and functioning safely. An electrician can check the pump for any signs of damage or wear and tear. They can also check the wiring for proper connections, insulation, and grounding. If the electrician finds any problems, they can recommend corrective action to ensure that the pump and wiring are safe to use. Submersible pumps used in lakes and ponds are subject to specific electrical safety requirements due to the inherent risks associated with water and electricity. The National Electrical Code, or NEC, provides detailed guidelines for installing and maintaining these pumps to minimize the risk of electric shock and other hazards. Section 680 of the NEC specifically addresses electrical safety requirements for swimming pools, fountains, and similar installations. While a lake is not explicitly mentioned, the general principles of Section 680 apply to any body of water where electrical equipment is submerged or located nearby. Section 680.51 covers permanently installed swimming pools and wading pools. This section requires that all electrical equipment associated with the pool, including pumps, lighting, and heaters, be GFCI protected. The GFCI protection must be provided by a circuit breaker or a receptacle with GFCI protection. The purpose of GFCI protection is to quickly interrupt the flow of electricity in the event of a ground fault, which can occur when electricity leaks from a faulty piece of equipment into the water. A ground fault can create a dangerous electrical shock hazard for anyone who comes into contact with the water. In addition to GFCI protection, Section 680 also requires that all electrical equipment associated with the pool be properly grounded. Grounding provides a safe path for electricity to flow back to the source in the event of a ground fault. This helps to prevent the equipment from becoming energized and creating an electrical shock hazard. The grounding system must be installed in accordance with the NEC and all applicable local codes. The NEC also specifies the type of wiring that can be used for pool equipment. All wiring must be approved for wet locations and must be installed in a manner that protects it from physical damage. Underground wiring must be buried at a minimum depth specified by the NEC. The NEC also provides guidelines for the location of electrical equipment around pools. The electrical equipment must be located at least 5 feet away from the edge of the pool, unless it is specifically designed for use in wet locations. This helps to prevent accidental contact with electrical equipment while in the water. In addition to the NEC requirements, many local jurisdictions have their own electrical codes that apply to pools. These codes may be more stringent than the NEC, so it is important to check with your local building department to determine the specific requirements in your area. Proper installation and maintenance of electrical equipment around pools is essential for ensuring the safety of swimmers and others who use the pool. Regular inspections of the equipment can help to identify potential hazards before they cause an accident. If you are not comfortable working with electricity, it is best to hire a qualified electrician to install and maintain your pool equipment. The depth at which an underground feeder or off cable is buried plays a crucial role in ensuring its safety and longevity. The National Electrical Code, or NEC, sets minimum burial depth requirements to protect a cable from physical damage, environmental factors, and potential hazards. The primary reason for burying UF cable is to shield it from accidental damage caused by digging, landscaping, or other activities. A shallowly buried cable is more susceptible to being struck by shovels, gardening tools, or even vehicle traffic, leading to damage to the insulation and potential electrical shorts. The NEC specifies a minimum burial depth of 18 inches for UF cable in residential areas. This depth is considered sufficient to protect the cable from most common types of physical damage. In areas where the cable is subject to heavy traffic or other potential hazards, a greater burial depth may be required. Environmental factors such as soil conditions, moisture levels, and temperature fluctuations can also affect the lifespan of UF cable. Burying the cable at the proper depth helps to protect it from these environmental stressors. For example, burying the cable below the frost line can prevent it from being damaged by freezing and thawing cycles. Additionally, the soil surrounding the cable provides insulation and helps to maintain a stable temperature, which can prolong the cable's life. Soil composition can also affect the rate at which UF cable degrades. Highly acidic or alkaline soils can corrode the cable's insulation, leading to premature failure. Burying the cable at the proper depth can help to mitigate the effects of soil composition. Underground feeder or off cable is designed for direct burial, meaning it can be buried directly in the ground without the need for conduit or other protective measures. However, it is still important to follow proper installation procedures to ensure the cable's safety and longevity. Before burying UF cable, it is important to inspect it for any signs of damage. Look for cuts, abrasions, or other defects in the insulation. If the cable is damaged, it should be replaced before being buried. It is also important to ensure that the cable is properly sized for the load it will be carrying. The cable should be sized according to the NEC and all applicable local codes. Overloaded cables can overheat and cause a fire. When burying UF cable, it is important to avoid sharp bends or kinks in the cable. Sharp bends can damage the insulation and reduce the cable's current carrying capacity. The cable should be laid in a smooth, gradual curve. The soil surrounding the cable should be free of rocks, debris, and other sharp objects that could damage the insulation. The soil should be compacted around the cable to provide support and prevent it from shifting. After the cable has been buried, it should be marked with warning tape or other markers to indicate its location. This will help to prevent accidental damage to the cable in the future. Proper grounding is essential for the safe and reliable operation of electrical systems. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip the circuit breaker or fuse and prevent electrical shock hazards. The NEC specifies the requirements for grounding electrical systems. The grounding system must be installed in accordance with the NEC and all applicable local codes. There are two main types of grounding systems: grounding electrode system and equipment grounding system. The grounding electrode system provides a connection to earth. This connection helps to stabilize the voltage of the electrical system and provides a path for fault current to flow back to the source. The grounding electrode system typically consists of a ground rod, a metal water pipe, or a concrete encased electrode. The equipment grounding system provides a path for fault current to flow back to the source from the non-current carrying metal parts of electrical equipment. This helps to prevent these metal parts from becoming energized and creating an electrical shock hazard. The equipment grounding system typically consists of a grounding conductor that is run along with the circuit conductors. The grounding conductor is connected to the metal parts of the equipment and to the grounding electrode system. The size of the grounding conductor must be in accordance with the NEC. The grounding conductor must be large enough to safely carry the maximum fault current that could flow in the circuit. Proper bonding is also essential for the safe and reliable operation of electrical systems. Bonding is the process of connecting together all of the non-current carrying metal parts of an electrical system. This helps to create a low impedance path for fault current to flow back to the source. The NEC specifies the requirements for bonding electrical systems. The bonding system must be installed in accordance with the NEC and all applicable local codes. All metal raceways, enclosures, and equipment must be bonded together. The bonding connections must be made with approved bonding connectors.